Hey, ARECE 4260, welcome to the last segment of our course, Short Columns. On the syllabus, after this, we were going to do footings, but because we missed that 1 week, that extra week of spring break due to COVID 19, that got deleted from the course. I'll post videos for footing design, so I'll put those on the YouTube channel uh, so you could see that. It's hard to believe, but we're starting our fifth week of online learning. We've done 1 month already online. And if this was a 15-week semester, we'd be on entering week 14 out of 15. But it's a 14-week semester now, and we're entering week 13 out of 14. Either way, if you were to convert that to a marathon, if this 15 weeks or 14 weeks was 26.2 miles, we're right around mile 22, 22 and a half. And if you've ever run a marathon, right around then, or maybe even a little earlier, is when you hit the wall. And it's been taxing. In a normal semester, we'd be tired, but this has been pretty hard. And so, good for you for hanging in there. We're on the last little bit here, and we're gonna push through and finish. And what we're gonna do is start with some basics about short columns. I'll define what a short column is, and then we'll end today's little segment with how to calculate the pure axial capacity of a column, which won't actually be that useful for design, but it's a good introduction to the topic. And first of all, let's talk about what columns are. Columns are the vertical elements in a building, and their primary function is to carry axial load. There's floors and floors above them carrying and those loads go on the slab, to the beams, to the girders, and eventually into the columns. But columns also have moment in them. We are not going to talk about seismic design in this class, but seismic load resistance is actually kind of a really, really important thing for columns beyond the scope of this class. Maybe I'll touch a little bit on that at the end. But columns, as shown in this picture here, have axial load and moment. And you say, how do they get moment? And so here we have a frame, and if you were to load just that one bay there, and the columns to the left or right of that, they would get moment on them, right? Because there's moment on the ends of the beams, the negative moment there, and Newton's second law that's F equals ma. First law, body keeps on doing what it's doing. Newton's third law, equal and opposite reactions. There's a moment on the end of that beam, so the end of that beam is putting a moment on the column, right? So you will get moment on the column. And so on the left here, you see an axial load and a moment. And if you're good at statics, you realize that force and moment can be replaced by a single force that's out to the side. And we see that's eccentric. And E is the eccentricity. And if E actually, that distance, if it's m divided by p, the moment is p times E. Well, p times E, if E is m over p, p times E will be m. And so you can see that these two are equivalent systems. And we'll talk about this a lot. We'll talk about the eccentricity of the load on the column. Now, the load isn't physically offset. What it is there's an axial load and a moment, and that's equivalent to putting that axial load offset on the column. And the way the numbers work out, it could be like this. It could appear to be off of the column even. When we talk about columns, there are two major kinds of columns that we want to talk about, tide and spiral. And so I should have got photos, but you can get a picture of what these are like. So spiral columns are they have these reinforcement or sometimes wire that's just spiraled up, okay, and you have the bars around them, and typically they're round, but you can get rectangular spirals. I've seen a machine that does that. Um, or you can just have the bars and put ties around them. They're all individual ties, and that's called tied. Okay? And you can obviously also get circular ties. So typically round columns have spirals, but round columns can be tied. And, and typically square columns are tied, but I have seen square spirals. Um, and so the main thing is it continuous spiraling up? That would be spiral, and or are they individual hoops tied up going up the column? And so before I show the next slide, which of these do you think would perform better? A continuous spiral going up, sort of like a slinky, or individual bars tied around? And if you guess that it's the spiral, you're correct. And while they have about the same strength, the key advantage of this schematic graph here is that the spiral columns can deform much, much more. And this is particularly important for seismic response. This is really important, the drift capacity of the piles. And this is reflected in the strength reduction factors, or the phi factors. The phi factor for a tied column is 0.65, and the phi factor for a spiral column is 0.75. And if you compare that to flexure was 0.9. And if you remember, we talked about the phi factor for beams, and way back then I said just keep the strain to this level and you can always use 0.9. Well, if you end up getting lower and lower tension strain, the compression controls, and this is what happens. If you have a compression controlled member, the phi factor goes from 0.9 all the way down to 0.65 or 0.75. And that makes sense because if you're tension controlled, the steel controls the behavior, and steel is well behaved, and you can get a phi of 0.9. But if it's compression controlled, there's much more variability and much more risk involved in a compression controlled section, and the phi factors are lower, significantly lower. And I said this is short columns, and what I'm referring to is that if you have a long column, it can do something like this, right? That's, in this is always mirror image, so it's hard for me to do. Okay, in the worst case scenario, to buckle, but even if it's reasonably strong and it only goes out a little bit, okay, here. Okay, so let me try and do that. And pushing down, let me do that again. So you push down. This force now, when it starts to buckle over, let me see if I can, there we go. That force is an amount delta away from here. And that's a moment, right? P times delta. That will cause a moment. So before it sways over, delta 0, and whatever you calculated the moment to be, that would be the moment. But if the column is slender enough and it can move over, I'm trying to keep my finger vertical here, but if it can move over, there we go. If it can move over, it's P times delta. Oh, just a minute. I think, let's see. No, I was going to say webcam only to blow up my picture, but I can't do it. But anyway, this having this axial load move over and then causing a moment because of P times a moment on delta, it's an extra moment, and that's called the P delta effect, P times delta. That only happens if you have something very slender like this. If you have something like this, let me get away. I can only make it bend in and out. I'm trying to make it bend this way. So if you have something that's not slender, okay, it's thick, uh, it won't happen. There will be no P delta. Well, we don't say thick, but we say short, okay? And so the column is short, meaning it won't have a P delta effect. The moment you calculate is the moment you get. You do not get this extra moment due to P times delta. And typically, because concrete strength is not as high as steel strength, concrete columns often are short. We do have slender columns as concrete strength gets higher. But when something is really high strength, you can make it thinner and smaller. And if it's high strength, there's a chance for it to have P delta effect. That's why this is such a big thing in steel design. If you've taken steel design last semester, you did a lot about P delta effect in the columns. We will not have P delta effect in this course. We do have P delta effect in concrete columns, but beyond the scope of this class. Okay, I think I'll stop here for now. And next, what I'm going to do is talk about the pure axial capacity of columns. That'll be the next video.